Good morning to all. Today our topic is on COP of an ideal vapor absorption refrigeration. So we know already the COP of refrigeration means it is the ratio of the refrigeration effect to work supplied. So in this system, the vapor absorption system, the refrigeration effect divided by the heat supplied. How much amount of heat absorbed in the evaporator to the how much amount of heat supplied in to the generator. The heat is supplied to the generator, that is the input. The heat absorbed in the evaporator from the substance, that is the refrigeration effect by the evaporator. So let us discuss what is Q1. Q1 is a heat absorbed at absolute temperature T1 in the evaporator. T1 in the evaporator, that is the Q1. Q1 amount of heat is absorbed with a temperature of T1 in the evaporator. Q2, the Q2 is heat is discharged in the condenser at absolute temperature, that is T2. The Q2 amount of heat is discharged in the condenser at a temperature of T2. Next, Q3, the heat is supplied to the generator at an absolute temperature of T3. Amount of heat Q3 amount of heat is supplied to the generator at a temperature of T3. A temperature of T3. So here the temperature T3 is greater than temperature T2 greater than temperature T1. See, the temperature T3 is greater than temperature T2. Temperature T2 is greater than temperature T1. So the heat is received from the evaporator. The amount of heat absorbed in the evaporator and the amount of heat absorbed in the generator, that total amount is discharged in the condenser to the surroundings. Condenser to the surroundings. See once again, the amount of heat, the refrigerant, the heat is absorbed in the generator, heat is absorbed in the evaporator. The same refrigerant heat is absorbed in the generator. The total amount is discharged in the condenser. So that's why Q1 plus Q3 is equal to Q2. See here, what is Q1? Q1 is evaporator amount. Q1 is evaporator amount. Q3 is generator amount. So Q1 plus see here, Q1 plus Q3 is equal to Q2. Q1 plus Q3 is equal to Q2. See this figure. So the amount of heat, that is Q3 amount of heat sub in the generator, Q1 amount of heat in the evaporator. This Q1 amount and Q3 amount is rejected in the condenser. Rejected in the condenser, that is Q2. So this is a perfectly reversible system, and there is a initial of entropy of the system must be equal to final entropy after its change its condition. So that's why Q1 by T1 is equal to Q1 by T1 plus Q3 by T3 is equal to Q2 divided by T2. So Q1 is equal Q1 plus Q3 is equal to 2. So Q1 by T1, Q3 by T3 is equal to Q2 by T2. So sum of this entropy equal to sum of this entropy. Sum of this entropy is equal to this entropy is equal. So that's why it is a perfectly reversible. So COP of the vapor absorption refrigeration is equal to, it is a ratio of heat absorbed in the evaporator to the heat supplied to the generator. So that is, this is the input, this is the refrigeration effect. So the evaporator heat absorbed is Q1. So heat supplied to the generator, that is Q3. That is Q3. See, Q1 by T1 minus Q2 by, see here, Q1 plus Q3 is equal to Q2. Q1 by T1 plus Q3 by T3 is equal to Q2 divided by T2. Q2 divided by T2. See here, this Q2 equal to Q1 plus Q3. Same, I substitute here, Q1 by T1 plus Q3 by T3 is equal to, this Q2 is equal to Q1 plus Q3. So Q1 plus Q3. So I simply write it as this one, same step, same as here, Q1 by T1 plus Q3 by T3. So here I write here Q1 plus Q3 divided by T1. I have written simple uh, step Q1 by T1. So Q3 by T3, T2, sorry, Q1 by T2, Q1 by T2 plus Q3 by T2. So here see, to simplify these steps, Q1 by T1, same I write here same as it is. So this is Q1 by T2, take left side, so that's why it is minus. Next one Q2, Q3 by T2, I write this side, right side. So this Q3 by T3 is taken as right side. So it is most toward this side, that's why it is minus. So Q1 by T1 minus Q1 by T2 is equal to Q3 by T2 minus Q3 by T3. So in this both side, left side and right side, Q1 is common in from left side, Q3 is common in right side. So I take a comma, so Q1 outside, so Q1, whenever Q1 outside, this one is 1 by T1 minus 1 by T2 is equal to, so I am take outside Q3, so 1 by T2, 1 by T2, so 1 by T3. Now this is the final step. Next, we know already the refrigeration effect COP of vapor absorption refrigeration is equal to, that is Q1 by Q3. Q1 by Q3. So Q1 by Q3. So this 1 by T1 minus 1 by T2 is goes to as a denominator, and this 1 by T2 1 by minus 1 by 3 as a numerator. So I written it as a simple simplification, this one, this like, so T2 T3 is numerator, so T3 is goes to this side minus T2 divided by T2 minus T2 into T3. So this, to simplify this one, T2 minus T1 divided by T1 minus T3, T1 minus T3. So finally this is the, after simplification, this is goes to upward direction, cross multiplication. So T2 minus T3 divided by T2 into T3. So this T1 and T2 goes to upward, T1 and T2 goes to upward. So T2 minus T1 is downward. So the finally T1 into T2 divided by T2 into T3. So this is the same as T2 minus T2, T3 minus T2, T2 into T2 minus T1. So finally in these steps, both numerator and denominator T2 T2 cancel. Finally T1 by T3 into T3 minus T2, T2 minus T1. So now This is the final step for the COP of the vapor absorption refrigeration system. We know already. So T1, that is the temperature in the evaporator. T3, this is the temperature in the generator. This is the temperature in the condenser. That's why TE, so T3 is the temperature in the generator. So T2 is the temperature in the condenser. T1 is the temperature in the evaporator. That's why I written it here as TE by TG into TG minus TC divided by TC minus TE. So if you substitute the temperature values of this evaporator, generator and condenser, then we will get the COP of the vapor absorption refrigeration system. So thank you.